Hey there, everyone, it's Alejandro, and welcome back for day 196 of me doing the Daily LeetCode challenge that I reached 1 year's worth of green contributions here on GitHub. So today is promised for January 28th, 2025. Without further ado, let's get straight into it. Okay, today we get LeetCode medium problem 2658, maximum number of fish in a grid. First thing I see is the word maximum, which means we're probably going to do DP, greedy, or divide and conquer. Okay, you're given a 0-index 2D matrix grid of size m by n, where RC represents a land cell. Oh, okay, it's going to be another one of these. All right, number of islands type problems. A land cell if grid of RC equals 0, a water cell containing, this many fish if grid of RC is greater than 0. Okay, so land of 0, otherwise number of fish. Okay, okay. A fisher can start at any water cell RC and can do the following operation any number of times. Catch all the fish at cell RC or move to an adjacent water cell. Return the maximum number of fish the fisher can catch if he chooses his starting cell optimally, or 0 if no water cell exists. Wait, so can he only catch it in one thing? You can only move to adjacent water cells, right? Or if he chooses his starting cell optimally, is it not just the max of inside the grid then? Right? Well, here it's 7. Oh, no. Ah. Oh, okay. If anything, it's just going to be connected components, right? It's just going to be like, okay, essentially the zeros are land cells that break barriers of things, and essentially, or even better, it's basically just max area of island, right? This is just max area of island. Where, yeah. Okay, this is easy. Land equals 0. For I in range, here we'll say m comma n equals length of grid of 0. I'm pretty sure this is, yeah, because here it's like either 3 or 5 or 7 or 5, right? Right here it's like, okay, let's predict. Here it's 1. Okay, so it's going to be 1, right? Yeah. Oh, and m and n are tiny. You could have made it 10 to the 5 and this would still work because it's just number of islands. Okay, this is a really easy, what's the acceptance rate on this one? Okay, 61% and so on. Oh, and it has hints if we need it. Okay, if I don't misunderstand things, this is basically just like, okay, look at components, and essentially from a thing, you can catch the fish at cell RC, or you can move to any adjacent water cell, right? You can start at the cell, yeah, 1, 0, 1, 2, 3, right? Yeah. Like 3 fish, then move to cell 2. Yeah, so essentially you want connected components where it's like, separated by islands, or like, this is one connected component, and then you can catch all the fish in that connected component, right? So it's basically just maximum area of an island, right? Okay, here we'll do for I in range m. For j in range n, we'll say, if, here we'll just have a visited cell. Visited is equal to set. If grid of ij fish here we'll to do use walrus operator. Here I'm going to use it as a to do because I don't want to grid is equal to I and j. I don't want to screw myself with things like that and then lose time because of it. So here we'll do if fish equals 0 or I comma j. Here we'll do if grid of ij equals 0 or land, I should say, or I comma j in visited to do mark cells as visited by turning them into land, i.e. 0 cells, right? Just to make things faster later on. So here we'll say that, and we'll continue, right? Otherwise, num fish equals 0. Here we'll say, here we'll have directions is equal to 0, 1, 0, negative 1, 1, 0, negative 1, 0. Right? Here we'll say numfish is equal to 0. Q is equal to collections.deck. And here we'll just have Sorry. Yeah, if anything, I'll just do that. If grid of ij, yeah, well, we'll use a visit set for now, and then we'll, okay. Let's not overcomplicate our lives. Here's just I and j. Here we'll say visited.add I, j. And then here also we'll say, while length of the queue is greater than 0, x, y equals q.pop left, numfish plus or equal to grid of xy, assert grid of xy is greater than 0. Here we'll say visited equals grid of ij. Yeah, we'll just do things in this order. Okay, well we'll just make our life simple for now. Right, or okay, it's just because I want to do visit cells. Okay. We'll say once we visit / consume a cell, we will set it to a land cell, effectively mark it as visit. So here we'll say numfish is equal to grid of ij, equals 0, equals land. Q equals collections.deck of ij. You'll say, or here we can just say numfish is equal to 0. Yeah, we'll visit the very first one. Okay. I'm just having trouble on this. Okay, I just need to go, right? Stop worrying about implementation details. They literally don't matter. If anything, I can even just use a visit set. It's fine, right? So here, just I have the very first one. I set it to a land. Numfish plus or equal to xy. We will say for neighbor, for dx comma dy in directions, we will say neighbor x equals x plus dx, y plus dy. Neighbor x, neighbor y is equal to neighbor. Here we'll just say this. If in bounds equals lambda x comma y, 0 less than or equal to x less than m, and 0 less than or equal to y less than n. There we go. If not in bounds, neighbor x, neighbor y, continue. If grid of neighbor x, neighbor y equals land, continue. Otherwise, numfish plus or equal to grid of neighbor x, neighbor y, grid of neighbor x, neighbor y plus or is equal to land now. And here we'll say q dot appends neighbor x, neighbor y. All right, continue the search. Right? And then here we'll say if res less than numfish, res equals numfish. Or here we'll have res equals 0. At the very end, we'll do return res. Okay, let's run something like this. Okay, that's accepted. Let's submit. Okay, there we go. Completion streak 196 days. Consistency is key. See ya tomorrow. Okay, this was a nice and short, easy problem for us to get started with. Okay. Yep. Yeah, if inbounds, grid of neighbor X. Yeah, if not inbounds, continue. Okay, here I want to do something like this. Yeah, this is fine. This is fine. Oh yeah, here I can say if num fish like this. No, that doesn't work. Yeah, okay. I don't know how to use the walrus operator. Never mind. Yes, this is good. This is good. If it's equal to a land cell, we're chilling. Otherwise, get the number of fish. Get the queue set up. Here we can even just make this a stack, right? Here we'll have a stack with just I, j, and here we'll replace queue with stack. And here we'll just do stack.pop, right? Something like this should work as well. Yeah, here we'll do if not inbounds. My bad. Unknown network error. Classic. Okay, well, I'm going to copy my code. I'm going to refresh. I need to log in or sign up. Okay, you know what? Give me 1 second. I'll do that right away. I'll be right back in literally just 1 second. Okay, sorry about that. I'm back. I'm guessing that since I'm at my friend's board game place, it just forgot my creds and so on for a second. So okay, no worries. We just logged right back in. Okay, but now it's not gonna let me control Z whatever I was doing, right? Okay, well, not a problem in the world. We'll just get rid of that. Yep. Yeah, so now with a stack it should work, right? Yeah, it still works with a stack. That might make us a little bit faster. Oh, okay, makes us much faster, which is exactly what we love to see. Yeah, okay, this is just a classic. This is literally the same problem as this guy. It's the same problem as this. It's the exact same problem as this. Okay. So as always in all my videos, I do a quick recap of how I was able to solve the problem. So for this one, as I was just explaining, it is exactly pretty much the same problem as max area of island from the Nico 150. So I was able to do it pretty much immediately. Essentially, the whole idea is that as a fisherman, you essentially want to maximize the number of fish you collect. So what does this mean? Essentially, you're allowed to start at any cell, and wherever cell you start from, well, you have to start from a cell. You're essentially able to pick up all the fish that are in that cell and move to any adjacent water cell, right? Where a cell is a water cell if its value is greater than 0, right? If its value is equal to 0, it's a land cell, right? So essentially, if you look at something like this, then essentially, if you start, you must start on a water cell, right? If you start on a water cell like this one, right, you can pick up 2 fish here, and then maybe you can pick up the 1 fish here, but you can't go here, can't go here, can't go here, can't go here, because they're all land cells, right? They're zeros. And so essentially, you have your own connected component here of water cells, and essentially you can get all the fish in that connected component of water cells, right? So the problem really becomes grab all the connected components worth of water cells and essentially compute which one you can get the most amount of fish in, right? And the amount of fish will essentially be the sum of the values in that connected component, right? And turns out that this is the same thing as a max area of an island, because a max area of an island, basically land cells are like 1s and water cells are 0s, and essentially you want the maximum area of an island, which is the number of elements in that island, right? Which is basically summing 1 over over and over and over. Here, instead of summing 1 over and over and over, you just sum the cell values themselves, right? But it's like, if this problem was like, just ones for the fishes all the time, it'd be basically the same thing as max area of an island. I guess technically by that respect, it's more difficult than max area of an island, but really it's pretty much the same problem, right? But what you have to realize is that like it sounds hard and complicated, like, oh my gosh, I have to separate by connected components and so on. No, you can just do the classic little number of islands approach, right? Which is like loop through every single index in the grid, and if it's not been visited and it's not a land cell, then it's like, okay, it's a new water cell inside of its own component. Let's expand and fill the entire component and take the sum of all the fish values inside of that component, and that's the number of fish there, right? And when we do that, we'll just say, okay, if the number of fish is greater than our current result, we'll set result to the number of fish because we want, the maximum sum out of any component, and there we go, right? And in terms of how I do this, again, I say, okay, 0 is a land cell, grab the dimensions of the grid, the directions, we can go up, down, left, or right. Here an inbounds function that checks whether or not, some coordinates is in bounds, right? So here I could do, here I could get rid of this. If it's not the case, that check if in bounds first. Right, so if it's not in bounds, then we continue. But here we can just use De Morgan's law. Yeah, this should be neighbor x, neighbor y, just to make things a little bit faster. And here we can, okay, let's distribute this not. So it should be not of this or that. So it should be or this, right? And here we can write this a little bit nicer. Neighbor x this or neighbor y. Yeah, not in bounds, so ignore. So yeah, here we can just do if neighbor x less than 0, or neighbor y less than 0, or yes, I'll run it. Okay, I mean, honestly, this makes the code a little bit uglier. Maybe we just get a little bit of a faster runtime, which I usually like to try and do and so on, but yeah, and not even, right? So you know what, we'll just put it back to my beautiful lambda inbounds function. Sorry, this is whenever I can optimize O1 things, I like to do so, but here I'll just chill out. We just have a nice inbounds function. Let's keep the code nice and concise. So like, okay, we have a function that essentially tells us whether a coordinate pair x, y is in bounds or not. So we'll just use that as is and leave it untouched, right? So we'll just leave it as such. And so yeah, okay, we're a little bit slower, whatever, and so on. O1 details don't really matter that much. Well, they do in terms of the LeetCode stuff and so on, but that way, the code is a bit more clean because I have an inbounds function, right? But otherwise, essentially, it's like I'll loop through every single coordinate inside of the graph. So here I'll like do for I in range m, for j in range m. So first of all, I'll see, okay, if it's a land cell, we'll ignore it, right? We don't want the fisherman to start at a land cell. And also, instead of keeping track of a visited set, what I'm gonna do is whenever I want to mark something visited, I'll make that cell a land cell, right? So that way, if I, let's say that, for example, here I look at this component, right? And I'm like, okay, let's expand everything. Here's like, okay, the sum is 3. Then when I get to this one again, it's like, oh, I want to expand the whole thing and so on. Well, we don't want to do that work, right? Because we've already expanded the full component from here, right? Worst case, everything is a component, and if for every single IJ pair, you end up like, doing a full traversal of the graph, then it's like quadratic in terms of the input size of m times n, right? Which you don't want. You want it to be linear in terms of that. So what you do is essentially you mark all the nodes inside of a connected component that you search through as visited so that you always ignore them in the future. That way you only ever visit every single element inside the grid only once, right? And instead of using a visited hash set, here I just like, okay, whenever I visit an element, I'll essentially make it a land cell, right? So that way it's like, oh, if it's a land cell, it's either because it originally was a land cell or because I've already visited it, in which case it's like, okay, I just want to ignore it, right? it's already been handled basically. And so here otherwise I say, okay, we're not in a land cell, so here which means it's not visited as well, because here whenever we visit something, we'll purposely make those things land cells. Right here, maybe I can just do mark visited, just to make it clear. And there we go. Okay, nice. And here it's like, okay, here numFish will be equal to, okay, the number of fish in that thing. We mark it visited again, right? Mark visited. And then here's like, okay, otherwise we're going to start exploration, right? We're going to go from IJ, and we're essentially going to go and explore every single water cell that we can touch by going either left, right, up, or down from our current position and onwards from there, right? We'll expand the full connected component of water cells that we can, right? Which might be just one cell, it might be multiple cells, right? For example, in these cases, like, you know, here's a length 2, 1, here's a length 2, 1, here's a length 2, 1, and here's a length 2, 1, right? And those are all the components, right? Obviously, like, you know, something like this can't touch the ones in here because it's like here it's blocked by zeros and zeros, edges, and so on, so I cannot reach it, right? Where zeros are the land cells, right? And so this will be just typical stuff where it's like, okay, pop, you know, the position from the stack while the length of the stack is greater than 0. Then for every single direction, up, left, right, or down, we have the new position by going up, left, right, or down for every single one of the direction deltas, which is like, you know, 0, 1, 0, negative 1, 1, 0, negative 1, 0. And it's like, okay, first check that, like, you know, you're in bounds. So if you're out of bounds, then obviously ignore this neighbor. Otherwise, like, you know, okay, if it's a land cell, that means it's like I can't go to it, or it's already been something visited before and so on. Well, it won't be the case because that'll be in a different component separated by land cells, but oh, well, okay, right? Like, for example, 2, I might look at 1 and be like, okay, that's a valid neighbor. And then from 1, it's like 2 is a valid neighbor. No. We're going to set things as visited, or i.e. land cells, so that we essentially don't go in an infinite loop, right? Because here, if I remove this, I bet you that will, okay, really? Unknown network error again? But yeah, I bet you we'll go in an infinite loop here, right? So yeah, here we'll get into a time limit exceeded problem, because again, we don't want to allow ping ponging like this and so on, or memory limit exceeded, because I keep appending stuff into a stack, right? But now if I put that condition in there, everything is nice and bing chilling, right? So that way, essentially we just want to mark things visited. It's just the way that I mark things visited is by setting things to land cells once I'm done with them, right? So if it's not the case that it's out of bounds and it's not a land cell, then it's like, great, it's a water cell, right? So what we're going to do is say, okay, we're going to consider this water cell. We're going to add the number of fish in that water cell to the number of fish in a current connected component, so numFish plus recursive value, right? We set numFish instead of this component because it was not a land cell initially. Then we'll say, okay, we'll mark this guy visited, so we'll set it to a land cell, right? And here we'll append it into our stack for continued exploration, right? So that way it's like, if there's more undiscovered water cells from that point on, we'll discover them, etc., right? And we'll keep exhausting until we found every single water cell inside of this connected component, in which case we'll have, you know, mark them all as visited by setting them to land cells. And here we'll have numFish be set to, like, you know, the sum of the values inside of that connected component of water cells. And then here we'll say, okay, we have a result which is initially 0. If it's smaller than the number of fish that we found in this component, then we'll set res to be that numFish, right? So essentially this is the same thing as doing, like, you know, res is equal to max of res comma numFish, right? Same thing. So here we'll just do that. And then at the very end, once I've done it for, once I've traversed the entire graph, I've gone through every single connected component of water cells, computed the number of fish in those components, and then set res to be the maximum one of those. All that's left to do is just return res, and if we submit this, we'll see that it is a nice banger and efficient solution, which is exactly what we love to see. And so if you've ever seen, I know that my Nico 150 videos are not released for graph problems yet, so I guess it might not make as much sense. It's just that, yeah, I've already pre-recorded those video solutions and so on. But yeah, this is essentially, it's pretty much exactly this problem. So if this problem was confusing, I'd recommend starting off with this, and before starting off with this. Number of islands is a hugely important, influential problem in the LeetCode space. It's probably, like, you know, probably one of the most important problems you need to know. Like, this number of islands approach occurs in, like, so many problems, and not just LeetCode. Like, for example, you might be familiar with the Advent of Code challenge that I did for 2024. A lot of problems, like day 14, I ended up using this number of islands idea to essentially help me solve a problem that was completely unrelated to something like number of islands and so on, just because it's a pattern that comes up, like, so often. And so it's just a good pattern to know. And so yeah, obviously when you know that pattern, solving problems like this is like a piece of cake, 1-2 kaboom kind of combo. Wombo. So yeah, so hopefully that solution makes sense. And yeah, but otherwise, that's pretty much it for this video. If you did find it useful or enjoyable in any way, shape, or form, I would highly appreciate it if you left a like or a comment. But otherwise, I'll catch you in the next one. So till then, ciao, my friend. Bye-bye.